At the beginning of this video, you can see that he is at rest. Suddenly, he accelerates up to his highest speed that he travels. Acceleration is a vector quantity that is defined as the rate at which an object changes its velocity. An object is accelerating if it is changing its velocity. Now, for about a second, he travels at a constant velocity. Constant velocity means that the object in motion is moving in a straight line at a constant speed. He travels like this, and right after, he quickly decelerates to an abrupt stop. His acceleration is greater here than when he started because he is changing his velocity most in the shortest amount of time. For example, velocity equals change in distance divided by time. So if he traveled 6 meters in 2 seconds, his velocity would be 3 meters per second. Or if he traveled 4 meters in 2 seconds, his final velocity would be 2 meters per second. He has a greater velocity when he travels a farther distance in the same amount of time. Now taking those velocities, if his velocity was 3 meters per second and he started at 12 meters per second and it took him 3 seconds, what would his acceleration be? So acceleration, remember, equals change in velocity divided by time. So it would be the second and final velocity minus the first velocity. So it would be -9 divided by the 3 seconds. So his acceleration would be -3 meters per second squared.
As he pushes the box, there is a small moment before the box begins to move. This is due to the box trying to overcome the friction, or the resistance that is between the box and the ground. At this point, it's a static friction. Now that the box is moving, friction is still in play, though the applied force that the boy is putting on the box outweighs that friction. While at rest, the friction between the box and the ground is equal to the normal force, or the upwards force that the ground places upon the box. This normal force is also equal to the weight of the box, weight being the mass of the box times the acceleration due to gravity. And as the box moves, the type of friction has changed from static to kinetic.
The ball being tossed into the air is showing projectile motion and how objects work with air resistance. When the ball is thrown into the air, the force applied to the ball determines the initial velocity of the ball. The ball is slowing down until it reaches the max height when the velocity equals 0, right before it goes into the downfall. During the downfall, the ball is affected by the acceleration due to gravity, as well as the resistance acting on the other side. The air resistance is affected by the density of the air and the surface area of the cross-section of the ball. The air resistance determines the terminal velocity of the ball, which is the max velocity the ball can reach. When the ball reaches terminal velocity, it remains at that velocity until it lands or the velocity is terminated. Without air resistance, the ball would not reach terminal velocity and would speed up indefinitely until acted on by an unbalanced force, i.e. the ground. The air resistance is represented by F drag, and it is unequal to the force of gravity, which is why the ball does not stay suspended in the air because the forces are unbalanced.
As the boy begins to spin the chair in a circle, the chair is going to start experiencing circular motion. The circumference of a circle, which is pi times diameter, or 2 times pi times the radius, is equal to the distance it will go in 1 revolution. The velocity is now measured in revolutions per amount of time, or radians. The centripetal force is acting towards the center of the path like a dog on a leash who tries to run, but ends up going in a circle. Without the centripetal force, the object would not go in a circle because the velocity would take it in a straight line. Just like when he lets go of the chair, it continues in a straight line and not a circle. Centripetal force is a force that acts on a body moving in a circular path and is directed towards the center of curvature of the path. This happens with any motion in a curved path that represents accelerated motion. Once the centripetal force is added, the object ends up circling around the fixed point in the center, aka the boy. This force is dependent on the mass of the object, the velocity of the outer edge, and the radius of the circle. The radius of this circle is equivalent to the boy's arm because he is holding the chair with his arm straight out as he goes.